Hello and welcome to Empowered Learning. This video will be the first video in a series of videos that will cover SpringMass systems. The first thing that we want to do is show how a second order linear homogeneous ordinary differential equation, where all of its coefficients are constant, can actually be used to model a SpringMass system. And so if you're studying differential equations, if you're watching this video or needing to know this type of information, you're probably at a point to where you've already studied second order linear homogeneous equations, as well as second order linear non-homogeneous equations, where your force function is either a sine function, cosine function, polynomial, exponential, or the sum or product of any of those two or more types of functions. And so we see that one of the major applications of these types of equations will be the SpringMass system. And the SpringMass system basically is a simplified system that says we're going to model anything that vibrates or oscillates, and it has potential to have the oscillations decay over time. So that's essentially what the SpringMass system is trying to model for us. So the first thing that we're going to do in this series of videos will be to derive a simple SpringMass system to understand how these types of systems relate to a second order linear ordinary differential equation with the constant coefficients. The second thing that we'll do is we'll take time to review the three well-known cases of a second order linear homogeneous ordinary differential equation and see how those three cases compare to the four cases that we're going to study within this body of knowledge in coming up with all the different variations of the theme of responses for a SpringMass system. Okay, so essentially we have three cases for preliminary knowledge that we need to be able to model the SpringMass system, and we're going to break that up into four different cases for this particular situation. In the latter videos that I'll have, we'll be going over a set of examples that will sort of showcase all the different types of responses that we get for SpringMass systems. And so I've broken it up this way because if you kind of dig in deep into this particular subject, like I'm going to attempt to do here, you're going to see that these videos can get kind of long. And I want to break it up to where they're still going to be long anyway, but I want to break it up just to make sure that you get enough for whatever it is that we're trying to cover for that particular point in time. So what we're trying to cover is complete before we move on to the next thing. All right, so let's go ahead and look into our SpringMass system. And so I've done my best to draw a little SpringMass system over here, and I'm going to describe what I have in it, what it is that I'm trying to accomplish as far as a model, and then we'll go into deriving the equation that we need to model this. So the first thing that you see here is that we have a spring, okay? And the spring that we have here is going to be a spring that follows Hooke's law from physics. Basically what that means is that we're going to say the force of my spring is going to be equal to kx or kappa x, and I'm actually going to use the Greek letter kappa for that, which is k in English. So we'll have that, and x is going to be the displacement. Okay, so that's how you've normally seen it. We're going to change this up a bit because of the fact that we're calling position a function y and its independent variable is t. And we know that whenever we deal with Hooke's law, this x here is actually the distance from equilibrium. Okay, so if I change this up in how we're actually going to use it, it'll actually look something like this, where we know the y sub I would be our initial position, and y sub f would be our final position. Okay? So if we assume that the mass is at equilibrium, meaning that this spring is not stretched or compressed any, then we know that our initial position is going to be at 0. Okay. Our final position we'll just call that y, because whatever it is, we'll just call it y. So we'll look at this spring, the force of the spring, as just being kappa times y. Okay. So for now, we will just keep that there. Now, we also have in this system what is called a dashpot, a dashpot. And a dashpot is nothing more than a shock absorber. The purpose of the dashpot is for us to dampen the oscillations that we're going to get from the system by taking this mass here and making the mass move back and forth. Okay, so this is our dashpot right here. And we're imagining that we have a mass here and there's some motor that's attached to a pulley system, and it's basically making this mass bounce either backwards, forwards, or both. Okay. We're assuming here that there's going to be some friction with the ground, and we're assuming that there is some friction that's going to be, well, some force due to friction that's going to be acting on the mass due to air drag, depending upon how fast the mass will oscillate back and forth. Okay. So in saying that, we're going to simplify this model here to just talking about the force that will be applied to the system based upon the dashpot and the force that will be applied to the system based upon the resistance that we get from air, depending upon how fast the mass moves. Okay. Now, the force from the dashpot, this device that's here, remember, it's just a shock absorber, and what we can basically do is what we can basically think of it as is a container that either has some type of material, solid material, or fluid, or a combination of both. Normally, you'll have things like air, oil, hydraulic fluid. You could have sand. You could really have whatever you want. But the whole point is to get a material in there that is viscous enough to be able to die down the oscillations over time if you need that to happen. Okay. And normally with a shock absorber, if you're thinking about a car, if you were riding in a car, let's say you hit a pothole in the road, then that bump that you feel when you go over the pothole would actually be what we call an impulse type of force. Okay, so basically a quick burst of some type of force, of course, reacting to the fact that the car or that wheel has fallen into the hole temporarily. And so if we think about it that way, the dashpot here, what it's going to do is it's going to exert a force against that so that your car ride, even though you hit that bump, will be as smooth as possible. Okay? And one of the things that we know is that depending upon how fast you're driving, depends upon how much force will be applied to the wheel. In other words, how hard the bump will be whenever you drive over. Okay, so in that instance, we know that the amount of force is going to be proportional to velocity. Okay, so if we call our dampening coefficient gamma, and just so that you know, gamma would be a coefficient that is you find it out through experimentation. So basically, you do some measurements to see, well, hey, if I apply this kind of force to this situation with this setup, how fast will this force sort of decay and go to zero? And so the damping coefficient, gamma, is what we'll call that, will be a measure of that. And of course, it'll be higher for more viscous type of materials or fluids. And viscous is just another word for saying thick. So if our dampening coefficient is high, then that means that the material or fluid or whatever is very thick. If it's thin, then it's very small. Okay? And of course, it goes from 0 on up to whatever. So since we know that the force of the dashpot or shock absorber is going to be dependent upon the velocity, then we could rewrite this function this way, where it's going to be dampening coefficient times velocity. And since velocity is going to be the derivative of position, we could rewrite this way. Okay. Now for air, same thing. We know that the air drag is like, let's say if you take your hand, let's say you're driving in a car or whatever, and you stick your hand out the window, and of course the faster you're going, the more resistance you feel against your hand as you're moving in the car. If you're essentially walking, you feel virtually no resistance because you're walking slow enough to where you don't virtually have no air drag. Okay, so what I'm going to do here is we'll call this dampening coefficient gamma sub D. I'm going to call this one gamma sub A. And again, same kind of thing. We know air drag is going to be proportional to velocity. So I can go ahead and put the D there too. So I can look at this as dampening coefficient of air times derivative of position. So we've talked about force of the spring. We talked about the force of the dash pod. We just talked about the force of air here. And for simplicity, even though we have some force that's acting in the system due to the surface on these wheels here, what we're going to do is go ahead and just lump that up with the air right quick. Okay, and again, this is just to make the model simple. So we'll just include surface friction in this one, just as an assumption here. Okay. So the last thing that we need to do, now that we have force of the spring, force of the dash pod, force of air, we do have this external force, which would be, I'll say, the force of the motor. In general, we'll call this an external force. Okay, and we don't know what that's going to be. Okay, if the motor's not on and it's not really affecting anything or applying a force in the system, then it'll be 0. Okay, if it's the case where let's say like we have the car and we're driving it over a pothole and we have that short burst impulse type force, then it could be a constant value. Let's say like 5. Again, it could be that for a very short period of time. We could also have the motor on and just say that, hey, we want to apply 5 newtons to this system force-wise continuously from time t equals 0 to infinity. In that case, it'll just be 5 and it'll just last forever. Okay, whatever it is, we will deal with that part later. Okay, the important thing to know is that we do have to take into account of an external force, and here's where the non-homogeneous portion of dealing with those second order linear non-homogeneous equations comes into play, because what makes those equations non-homogeneous is essentially the external force acting on the system. So we have this. So we know that if we look at a system of forces, everything's going to have to balance out. So in knowing that, we know that our total force, which I'm just going to call Ft here, is going to have to be a sum of the force that's coming from my dash pot, force that's coming from the air, And remember that we're assuming that the force coming from air is also going to include the surface friction as well, just to make the model easier. We have the force of the spring, and we're going to have our external force, which for now I'm just going to call F motor. Okay. Now, if we were to go and actually fill in everything, we would have the right side of the equation will have something nice to represent it, but we don't have anything to represent the total force yet. But remember that Newton's law of motion says that force is equal to mass times acceleration. And of course, we know acceleration is the second derivative of position. So we could express our force as just the second derivative of y times the mass. And so now we have a way to express all the forces in terms of position y according to what this spring mass model I've drawn here represents. So with that being said, there's one other thing that we need to account for before we write this equation. Okay. So we know that if we're looking at the total force, there's going to be forces acting in certain directions. Now, whatever this particular force here is going to do, let's say, just hypothetically speaking here, that we apply a force that's going to go this way. Okay. Well, we know that this spring here is going to try to pull the mass back in the opposite direction. We also know that the fluid or material that's inside of this dash pot here, if we pull the mass away, is going to be working against that particular material, so it's going to try to fight back and do a force in the opposite direction as well. So I'm saying all that to say that if our external force is acting in one direction, then we know that our spring, force of our spring, dash pot, and air are actually going to be acting in the opposite direction. So here I'm going to put negatives here, and negatives here. Okay. The other thing that I'm going to do to simplify this even more is we're just going to combine these two forces here. We're going to add them and just say that this is going to be the force due to resistance, okay? And that's going to be resistance of surface, resistance for the dash pod, resistance of the spring mass system. So those will be all the resistances that we'll experience. And so we'll just simply call this minus gamma times dy over dt, where our gamma here will just be gamma A plus gamma D, meaning friction due to air and surface friction, as well as, dampening due to the air and surface friction, as well as dampening due to the actual material in the dash pot. So we will look at this particular resistance here. And what we'll do is take this and just say all this is equal to F resist. Okay. So now that we have that, I can write my force here for the total to be M times the second derivative of Y. And of course I wrote it in Leibniz notation here, but I'm going to do it in prime notation here. F resist will just be negative gamma times Y prime. And again, that takes care of both of these. Minus kappa Y. And of course, that's because of our force that's exerted by the spring. And then F motor, we're just going to just leave that as F motor for right now. Okay. And so if you look at what we have here, it looks like we have the workings of a second order linear non-homogeneous equation here. And to get it into a form that we're used to seeing, what we need to do is just add the F resist and F spring to both sides here. So if we do that, we'll have M y double prime plus gamma y prime plus kappa y equals F motor. And so here we'll go ahead and just change the name of this now. So I'll just call it F motor. I want to keep it as general as possible. And we will just call this the external force. And so essentially what we have here is a second order linear non-homogeneous equation, provided that we're thinking that the external force would not be zero. Okay? So if it's this, it would be non-homogeneous. If our external force was zero, then our equation would be homogeneous at that point. And so we see how this would actually end up, the SpringMass system would end up being a situation where we could model it with a second order linear non-homogeneous equation. Okay. Now, I want to come back up here for a second and sort of go over what all the constants mean and the assumptions and the units before we move forward here. So I'm just going to erase some of this and then we'll talk more about that. So in this SpringMass system, I know I have 12 kilograms here, and I have that because in the examples that I'm going to do to try to showcase all the different cases for a SpringMass system, I'm going to keep the mass to be 12 kilograms during that time. And so you'll see this same model over and over again in the other videos where we have these examples. Our spring constant will be kilograms divided by seconds squared. Our dampening coefficient of the dash pod will be kilograms per second. Of course, we assume that our mass and our spring constant will be greater than zero, and we assume that our dampening constant will be greater than or equal to zero. And of course, this F sub zero that you see here, this is the same as what I'm calling the external force. Didn't quite go so well there. The external force. Okay, or in this case, the force that's exerted on the system by the motor. Okay, so F motor, all this is the same thing. And so now that we know how we actually model the SpringMass system with a second order linear homogeneous equation where all the coefficients are constant, we now want to get into the different cases. So as I said before, we have 4 cases for the SpringMass system. These cases originate from the characteristic equation of the homogeneous solution of the SpringMass system. And if you recall from studying second order linear homogeneous equations where all of your coefficients are constant, you'll see here that it's the same as the characteristic equation for those types of equations. So by figuring out what is going on with all the solutions or roots of the characteristic equation of homogeneous solution for those equation types, we essentially can see what's going on in the SpringMass system as well. Now, much like the characteristic equation for second order linear homogeneous equations, we know that the roots, what those solutions look like, depend upon the discriminant. And so each of these 4 cases is going to depend upon what the discriminant looks like. Now, the thing that directly affects what the discriminant looks like is our dampening coefficient, gamma. And so we're looking at cases when gamma is 0, meaning that there's no dampening at all. So just imagine that we have a shock absorber that's just literally made out of air, not anything compressed, no material, anything like that. There's nothing in it. Okay. We have case 2, where our dampening coefficient is going to be in between these values here. Okay. So this is 2 times the square root of the mass times our spring constant. Okay. So we got mass times spring constant, take the square root of that, and then multiply that times 2. If you look at our discriminant here, which is gamma squared minus 4mk, notice that 4mk is the same thing as 2 times square root of mk squared. It's the same exact thing as that. So essentially what we're saying here is, when we want to look at cases where gamma is in between 0 and 2 times square root of m kappa, we're essentially saying that the discriminant is going to be negative, but it's not going to be as negative as it could be if our dampening coefficient was 0. And so what we're going to see here is that this is going to be the extreme case for no dampening. And as we move closer and closer to this value of 2mk for gamma, we're going to see that there's going to be dampening or decaying of our oscillations for values in here up until we get to this point. Case 3 is going to be a case where we essentially end up having our discriminant equal 0. And so in that case, our spring mass system is going to try to oscillate back and forth, but because the dampening of the dash pod is so stiff that it's not going to be able to make a full oscillation. And then of course, in the case where if we go beyond the value of gamma equaling 2 times square root of mk, then we know that the fluid or material in the actual dash pod is so viscous, it's so thick, that we're not even going to have oscillations at all. And what ends up happening is that for case 1, you have major oscillations. Okay. In case 2, you still have oscillations, but they're not as pronounced as in case 1. In case 3, you try to have an oscillation, but it goes to acting exponential. And then in case 4, you don't even, the system doesn't even try to oscillate. You're purely exponential at that point. So one way to think about these 4 cases is case 1 is a pure oscillatory type of environment for your, let me say, oscillatory type of response for your spring mass system. For case 2, you have primarily oscillatory response, but there is an exponential component that's going to be in there that's going to help make those oscillations decay over time. Case 3 will be the case where the thickness of the material that's in the dash pod is so much to where it will try to oscillate, but it's going to actually act more exponential than oscillatory, but it's going to start off oscillating or trying to oscillate. And then case 4 is purely exponential. The material is so thick that it just, if you do a sudden impulse external force on the system, it's just going to decay away exponentially, just like an exponential. So there'll be no going back and forth of the mass as it decays. So now that I've talked about these cases at a high level, let's go and look at the math to see what our actual responses will be based upon what the math turns out to be. So we see here that when we have no dampening, then of course our gamma here would be 0, this would be 0, so we just end up with, of course, a negative value under the square root sign here, which tells us that we're going to have complex conjugate answers. And since gamma is 0 here, we see that it's purely imaginary. And we know from studying second order linear homogeneous ordinary differential equations where all the coefficients are constant, we know that this is the same as your lambda plus or minus omega, where lambda is your real part, omega is your imaginary part. And since lambda is equal to 0, the response that we have for the homogeneous solution, this will just be 0. And of course, e raised to the 0, all of that is just 1. Okay. For the omega here, we call that square root of k, or kappa, or the spring constant, divided by m, which is the mass. And so what this ends up actually being is the natural frequency of the system. And of course, I define that down here. So what this says is that if I was to, and just to use a car analogy again, if I was to drive over a pothole with my car, the force that's going to be exerted on the spring mass system that's better known as the wheel and the shock absorber, of course, in the spring that's on that. So we would see here that if we just had that one force and then nothing else was applied, then the way that that particular mass or the wheel would oscillate back and forth before, let's say, the oscillations would stop, would act a lot like this. And for this case, since we have no dampening whatsoever, what this is essentially saying is that if I hit that pothole and I kept riding with no dampening, I would just continue to oscillate back and forth, or I would continue to bounce up and down in my car forever and ever and ever, because there's nothing technically in the system that's going to make me stop bouncing up and down, because I don't have any dampening in my dashpot or shock absorber. Okay? And we see that the math supports this because a homogeneous solution here would just be this. Okay? And so again, that's now just to make sure that this is clear, this is what happens if we have let's say no force on the system whatsoever. So homogeneous solution would sort of act like, all right, well, in the beginning, if we just do a short impulse on it, impulse force, and then it goes away, then for long periods of time, you essentially have no force on the system. This, if you want to use another example, think of it as you have you're playing the guitar and you want to hold the string and you hold it in place and then you let it go. Okay. And then once you let it go, no other force is applied, and it just kind of the string just vibrates back and forth on its own. And if we had no dampening, then that string would just continue to vibrate back and forth forever and ever and ever. So that's what we're seeing here with this homogeneous solution. So for case 2, we call this the underdamped case, where essentially our value for gamma, or our dampening coefficient, is somewhere in between 0 and 2 times square root of m times kappa. And so the main point here is that if we do the math for this, then we'll see that if gamma is in between these two values, then that means that my discriminant that we talked about originally is still going to be negative. And of course, if I flip these two expressions around, then that means that this expression will be positive. And that means we could express our roots this way. And all this is saying is that our roots are going to be complex again, but we have this part. In other words, we have a real part to our complex roots, whereas before we didn't. Okay? And it's that real part, because we actually have some dampening now, that's the thing that's helping our system to essentially make the oscillation that it was excited by for a quick burst of time, is going to make it decay over time. And so we see that our homogeneous solution looks like this, and we know this from second order linear homogeneous equations where the coefficients are constant. We know that. And so it is this portion that's here, the exponential part, that's being multiplied times this periodic, or what we call quasi-periodic function, because it's not truly periodic. And this is actually making the oscillatory part of our response decay to zero over time. Okay. So I want to expound upon our case 2 type situation here a little more, because there is a special relationship in between the natural frequency that we talked about before in case 1 and the period of our response for cases 1 and 2 for the SpringMass. And so without trying to get too technical here, the main thing that I want you to see is that the frequency that our SpringMass system could oscillate at for case 1 is going to be the largest or highest frequency possible, okay, for that SpringMass system. Our case 2 situation, since we actually have an exponential component here that is making our oscillatory part of our response decay away as time approaches infinity, we see that the frequency of the response whenever we have a case 2 type situation, that frequency is going to be smaller than this one. Okay. Now, what does that mean? So that means in case 1, whenever we have no dampening, that means that your mass is going to oscillate back and forth the fastest that system would possibly allow it to do. Okay. As we apply the dampening, that's actually going to slow up how much that mass could oscillate back and forth. And of course, we know that with the dash pod, we know that the amount of force that's applied is going to be directly proportional to the velocity of the mass, meaning how fast the mass is moving. Now, as the dampening takes effect in the system, the slower you go, the less resistance is, or the less force is going to be applied by the material that's in the dash pod. And so I say that to remind you that one of the things I said earlier was that whenever we have a case 2, our system is actually has a quasi frequency, a quasi period. Okay. So as time goes on, the amount of force that the dash pod applies, since the mass is essentially slowing down and oscillating less and less over time, then that means that the corresponding frequency and period is going to change for that too. Okay. So this is why for your case 2 situation, it really does depend upon how much dampening you have. Okay. For case 1, the dampening is 0, so it's going to oscillate the same no matter what. So let's say if I had a dampening of 2, that's going to be one type situation, or one, I guess, amount of dampening. But of course, remember that for the dash pod, everything is with respect to the velocity. Okay. So as the mass slows down, the amount of force you get from the dash pod is going to be less and less and less. Whereas in the case of case 1, the force coming from the dash pod is always 0. So no matter what the time is, the contribution of dampening, or in this case, the lack thereof, remains the same. And that's why in that case, our mass will oscillate back and forth at the same frequency forever and ever and ever. Whereas here, it won't do that. And that's why we call that particular response in case 2, it has a quasi frequency or a quasi period. That's why we say that. But regardless of what that frequency is or what it turns into over time, it still won't be as large as this one, okay? Now, it's important for us to know that because one of the topics that we're going to talk about in some of the other videos is the concept of resonance. And so resonance is an important thing because resonance can either be a good thing and cause us to actually experience some gains or design gains that we want in a system, or it could be a bad thing and actually destroy a system, okay? And we'll talk about that when we get to that point. But the main connection I want you to get here is that natural frequency that we talked about in case one for a given spring mass system with a certain spring constant and a certain mass, that is going to be the highest frequency that particular system can experience, which means that however fast the mass oscillates back and forth at that particular in that particular state is going to be the fastest that it would do. All right, so now let's talk about our case 3. So our case 1, just to kind of recap on that. So case 1, we essentially said no dampening. Case 2, we said that there is some dampening, but it's not enough to keep the system from not oscillating at all. Okay? Case 3 is the case where we're on the borderline of our spring mass system responding with an oscillatory type of motion versus an exponential type motion. And of course, we can see that because at this point, notice that we do not have any sine or cosine functions in our homogeneous response. And so what that's telling us is that we're essentially acting like an exponential at this point, okay? Now, what I'm going to do down here is I'm going to write the response for the case 2 situation, so you can kind of see what's going on here. And so what I want to show you is how we end up with case 3 based upon the frequency or the frequency of the spring mass system decreasing as this value gets closer and closer to here, okay? So I'm just going to finish writing this and then we'll get into it. All right, so we notice here whenever our dampening coefficient is equal to 2 times square root of mk, we see that we end up having this double root here. And of course, we know from what we know about second order linear homogeneous equations, this is going to be our homogeneous response, okay? So what happens is notice that we only have a real part for our roots. So if we wanted to write this in an imaginary fashion, it would look like this. So our omega that we saw in cases 1 and 2, now it's 0. So if we take that and actually replace omega with 0 here, got 0 here and 0 here, then you see that cosine of 0 just ends up being 1, and sine of 0 here just ends up being 0. So now that we see that cosine of 0 is 1 and that sine of 0 is 0, this just comes out to be e raised to the negative gamma over 2m times t. And since this is 0, all we have is just c1. Okay. Now, notice here that we just have this portion as if we were to take this and multiply it times that. we still have a C2T that needs to be accounted for. And I went ahead and wrote this here. Notice that this is a fundamental solution of our second order linear homogeneous equation. Okay? And since our root here was a double root, we know from the theory behind solving those kinds of equations that if we do reduction of order, we will have another fundamental solution, which is going to be t times e raised to the negative gamma divided by 2m times t in the exponent. Okay? And so this is where the other solution, the C2t e raised to the all this business here, comes from. Okay? And so that's why we're able to have those two separate fundamental solutions and why we can add them together to create a single solution. Now, there's one other thing I want to say about this before we move on, but I'm going to erase a bit so that we can have some room to talk about. So now that we understand how we get our homogeneous solution for case 3, I want to go back and talk about this whole notion of whenever we have a critically damped system, that is really the borderline in between the SpringMass system acting in an oscillatory manner versus acting in an exponential manner. Okay? Now, this T that is introduced here, from a physical standpoint or conceptual standpoint of what's going on, the T that's introduced in there is actually trying to act like the oscillatory part of the SpringMass system. Okay, so what you'll see in the examples that we do later with the graphs, you'll see that the function will start to try to act in an oscillatory manner, but what it's really doing is acting like the function y equals c times t. Okay, but then at some point we have this portion of we have this portion here actually acting along with this portion, but then since values of t are going to get larger and larger, this is going to act more and more like c times t versus this exponential here. Okay, and there's this balancing act that goes on in between the function acting exponentially versus trying to act linear. Okay, and so what essentially happens in a critically damped case is that what the function will do is it will die out, provided that the external force is 0. It will die out, so that means that over time the mass will go back to equilibrium. It's just that it's going to do it faster than it would have for case 1 and case 2 because of the fact that this particular term has got this part that's going to 0, but because this t is being multiplied by it, is actually making it go to 0 faster than it would if it was just like this. Okay. All right, so let's go ahead and move on to case 4. So for case 4, we see that this is what we call the overdamped case. And think of this as the material or fluid or liquid that is in our dash pod is so thick to where if we were to be driving in the car again and we roll over the pothole, we would essentially feel nothing. Okay, because what the dash pod's fluid would do is basically just absorb that, and of course, well, we may feel the initial bump, but it'll be as if it feels the bump and then afterwards we don't feel anything else over that. So we have no oscillation going on whatsoever. And what our shocks will do is just move really slow to eventually get back to where the car would be level. Okay. And so this happens whenever our discriminant here is greater than 0. And notice that our response for this will be purely exponential at this point. Okay. Now, this is case 4 for SpringMass system, but you recognize this as case 1 for second order linear homogeneous ODEs. Okay? So we recognize this as the case 1, okay, back in that preliminary section. So what I want to do now is I want to go back and try to compare the first 3 cases right quick so you can see how the gamma actually plays a role, or the dampening coefficient, or the dampening that the dash pot does in our SpringMass system actually plays a role in how the oscillations are absorbed and how those responses end up actually essentially leading to a case 4 type situation. All right, so to look at this comparison here, we want to remember that our roots actually come from solving the quadratic formula. And of course, this is the quadratic formula with the mass and the spring constant and the dampening coefficient from our SpringMass system. And to make the numbers easy, we're just going to let both the mass and the spring constant be 1. We also want to note here that whenever we talk about angular frequency, which is what our omega is going to be 2 pi times the actual frequency. And that actual frequency would be measured in hertz, which is cycles per second. And we know that that is actually going to be the imaginary part of our roots here. And that's what this is. And of course, this will be our natural frequency for our SpringMass system. Okay. So we also want to note that if we know that our frequency is f sub 0, then the reciprocal of that will be our period, meaning how long will it take for the SpringMass system to allow the mass to make one full oscillation. Okay. Now, what I'm going to do here is look at the dampening from 0 to 2. Okay. And so if we do that, we see that in the case where there is no dampening, of course, our discriminant is going to be the largest magnitude-wise that it would be. Of course, if we flip these expressions around, then of course, this is going to be the coefficient for the imaginary portion of our roots, which also is part of what we have for our natural frequency here. So I'll go back up here. That's just the numerator part for our natural frequency. So if we was to take this amount here and divide it by 2m, then what we would essentially have is our natural frequency, which is what this is. And so notice that in hertz, what we would do, since we essentially have omega is equal to 2 pi f, we're just saying omega divided by 2 pi is equal to f, and that's what we have here. So if we used to say take this divided by 2 pi, we would just get 1 over pi, and that would be the actual frequency in hertz. And if we take the reciprocal of this in hertz, we get what the period is. So as you can see, I've made the numbers easy, but this is a very slow moving mass, because essentially it's taking us a little over 3 seconds to have one full oscillation of the mass. And again, I just want to keep the numbers easy, so that's why these numbers look like how they do. So this is our case 1 situation here. Okay. So for our case 2 situation, we see that our dampening coefficient is in between 1 and 2. Okay. And of course, this is negative, but not as negative as it was here. We divide by 2 again and get the natural frequency. And as you can see, our frequency has gone down, okay, by, looks like almost like a factor of 2. It's not actually that, but it looks like it. So our frequency has gone down, so that means that the time that it takes for the mass to make one for oscillation has gone up. And so because of that, what happens in a case 1 situation, you would have a wave that looks something like this, whereas in a case 2 situation, it would look more like this. Okay? And notice that the period and frequency of the second wave is not consistent like how the first waves was. And then on top of that, we notice that the second wave is actually dying out as t approaches infinity. For our case 3 situation, we see that our discriminant here is 0. And since our discriminant is 0, that means that the numerator for the imaginary portion of our roots is 0, which means that our frequency, or natural frequency, now goes to 0, and hence we essentially have no oscillatory type motion. Frequency, actual frequency is 0, and then we know that the reciprocal of 0 doesn't exist, it's infinity. So from here, that's just basically saying that we never have an oscillation at all. Okay. And so we see how the math supports what it was that we were saying, as far as we are at the borderline of when our function switches from acting in an oscillatory type manner to it acting in an exponential manner. And so hopefully this short example here can kind of clear up what's happening with your response. From a wave perspective or a graph perspective, what would happen in case 3 is something like this. So let's say the graph would go up, but eventually it'll just start to do like this and die out quickly. Okay. So here you're oscillating a lot. Here you're oscillating some, but it's dying out. Here it tries to oscillate, but it doesn't make a full oscillation. And then with our case 4 type situation, what actually happens, and I'll just draw this over here, the response doesn't even try to oscillate. So it just literally just goes like that and just acts like an exponentially decreasing function the entire time. So I've taken the time to graph these in Desmos so that you can kind of see what this looks like. So of course, this is our case 1 situation here. You see that the system's response is oscillatory and it never stops. The case 2 type situation, and because the numbers are so low, so to speak, it's not doing what it would actually do if they were higher. So in all actuality, if we had higher numbers, it would act more so like this. Okay, but we see that we try to get at least one full oscillation in the case of the numbers being low before it starts to die out. Your case 3 situation, here we see that this little hump that you see right here is it's still trying to act oscillatory, but it just quickly goes away. And of course, I didn't do a case 4, but what your case 4 would look like is it would start somewhere, not sure where, but it'll just go like this. So you won't even see it try to kind of do like this and then go back down. It'll just act straight exponential the whole entire time. All right, so I know that this has been a long video, but we needed to establish some of the theory behind these SpringMass systems and modeling them using the second order linear homogeneous and non-homogeneous equations. So the next video that I'm going to do is just going to wrap up what we're talking about with the theory. We'll get into the concept of resonance, and then after that we'll start to do examples.